Okay. Okay, great. I think we're live now. Maybe let's give it one more minute, Sean, and I'll introduce you, and then we can start.
Not a problem.
Thanks.
Okay, great. I think we're live now.
Okay, I think this is a good time to start. Welcome everyone for our Safari live seminar, the first Safari live seminar of the new semester, let's say here at ETH. We're very happy to have Sean Lee here. Sean is going to talk about thinking outside the die, architecting the next ML accelerator of the future. He has been doing quite interesting work at Cerebras Systems. He's the co-founder and chief hardware architect there. And before Cerebras, Sean was a fellow and a chief data center architect at AMD. He was responsible for the architecture of the C micro line of distributed servers. He holds a bachelor's and a master's degree in electrical engineering and computer science from MIT. His primary interests are in high performance computer architecture, hardware, software, co-design in areas including transactional memory, networking, storage, and machine learning accelerators. In fact, he did his master's thesis on transactional memory, unbounded transactional memory. And I remember reading his works at the time. Today, he's going to talk about a totally different topic, quite exciting, and talk about Cerebras systems and chips. Sean, thank you very much for giving this talk, and we look forward to your presentation. Here's how we will handle the questions. Sean will give the talk, let's say uninterrupted. It'd be good if you can hold on to your questions till the end, and we'll open the floor for questions at the end. And we have 1.5 hours or longer if it's really needed. Please, Sean, take it away.
Thank you, Onar, for that introduction. As Onar said, I'm Sean. I'm the co-founder and chief hardware architect here at Cerebras. And we started the company with a vision to drastically change the landscape of compute for AI. And in today's talk, I'm going to share with you some of the outside of the box thinking that we believe is really necessary to meet the demands of ML in the future. For those of you who don't know us, Cerebras started in 2016, really just at the beginning of the modern deep learning era. And our mission is to solve the problem of AI compute by building the full AI accelerator solution. That's from the chip to the system to the software. And now we have engineers and customers all around the world. And really what an incredible journey the last few years have been for both us as a company, and I'm sure you guys can all agree, for the entire industry, because a lot has happened in the ML industry in the last few years. But I'm here because we believe we're really just at the beginning of what neural networks can do. And we're already reaching a pace where traditional approaches really can't keep up. In 2018, state-of-the-art neural networks had 100 million parameters. And that was really a lot. But in 2019, models like GPT-2 and Megatron, they were 10 to 100 times larger. And then in 2020, we got GPT-3 with 175 billion parameters. And in fact, just a few months ago, Microsoft announced their Megatron Turing NLG model, which had 530 billion parameters. That's 500 billion parameters. And there's really no end in sight. Tomorrow, we're going to want to run models with trillions of parameters. So when you step back, that was 1,800 times more compute in just 2 years. Let me say that again, 1,800 times more compute in just 2 years. And as a computer architect, when I see that, and for all of us as a community, when we see that, this is both exciting and it's daunting. So let's look at some of the ways that we've responded to this unprecedented demand from these ML workloads. So the exciting part is that we as an industry have been hard at work and we've seen some remarkable innovations. In fact, all of those models I just showed you, they wouldn't have been possible without some of these innovations. Here are a few examples. In just the last few years, we've been continuing to improve in process technology. From 16 nanometer to 12 nanometer, and now 7 nanometer chips are used daily. We've also seen advanced packaging technologies that enable, among other things, higher bandwidth memories. And we have lower precision numeric formats, such as FP16, bfloat16, as well as new data path designs, such as systolic arrays or tensor cores that improve compute density and power efficiency. So let's take a deeper look at these improvements. First, let's look at process. On the right, I've plotted the transistor density of GPUs over the past 10 years or so. And as you can see, the process industry continues to improve at an incredible pace. So Moore's law is not dead. And in fact, we see this trend continuing for the next several years at least. Next, let's look at some of these other innovations. And broadly speaking, I'm going to group all of these into a category I'm calling architecture and microarchitecture. On the right, I've plotted a metric, peak flops per transistor, again for GPUs over the last 10 years or so. And here I'm using this metric flops per transistor as a rough measure of architecture performance. And what's impressive is, as you can see, there's a very healthy increase and clear trend over time. In fact, it's keeping up or even outpacing Moore's law by a little bit. And for us as an architecture community, that's really refreshing to see because architecture matters. So that's the exciting part. If you look at those 2 years, we got a 2 times improvement from process technology from Moore's law, and we got about a 3 times improvement from architecture performance. But now the daunting part. In that same 2 years, from BERT to GPT-3, as we just saw, the ML demands increased 1,800 times. So that's a 300 times gap. And how did we as an industry meet that need? Well, it all came from system scale out. In fact, when OpenAI trained GPT-3, they used 1,000 GPUs. So when you step back, the performance gains over the last couple of years have been completely dominated by system scale out. So you might think that's the answer, right? The ML demands certainly don't appear to be slowing down. So perhaps we can just rinse and repeat the last 2 years and we can satisfy the next 2 years' demand, right? Well, let's imagine what that might look like. We get another 2 times improvement from Moore's law. We do have 5 nanometer and 3 nanometer in the pipeline. And perhaps another 3 times improvement from architecture and microarchitecture, maybe higher density compute data paths, maybe different numerics. And then lastly, another 300 times from system scale out. Is that possible? That would mean clusters with the order of 100,000 chips. While that's not technically impossible, I think we can all agree that it's not a practical way of achieving this goal. In fact, just the sheer cost, power, and physical footprint would be prohibitive. And perhaps most importantly, it turns out that relying on existing scale-out techniques are not as easy to deploy, and they're really not that scalable. And the reason is that fundamentally, giant neural network models, they need a massive amount of memory, compute, and massive communication to tie them together. So by trying to provide this with thousands of small devices, turns the scaling of all of these into distributed problems that are interdependent. And it becomes an explosion of distribution complexity to get them all to work together to solve a single training problem. And in fact, this complexity grows dramatically with the cluster size and becomes quite overwhelming at very large models. So instead, for all of these reasons, with the existing scale-out techniques, I think there may be another 10 times improvement, but not much more for scale-out. That would give us cluster sizes on the order of 10,000 chips, maybe. And in fact, we're already seeing some evidence of this. When GPT-3 was trained, it was on 1,000 GPUs. And a few months ago, when Microsoft announced their MT-NLG model, that was on 4,000 GPUs. But we believe that this scale-out trend isn't going to continue much further with the existing techniques. So where does that leave us? With the current approaches, the industry as is possibly has a path to another 60 times improvement in the next 2 years. But the ML demand is growing at a rate of 1,800 times. And that is the grand ML demand challenge in front of all of us. We must find ways to substantially improve across the board, to improve process beyond Moore's law, to improve architecture by orders of magnitude, and to improve and simplify scale out dramatically. All of this is going to be required for us to have any hope of keeping up with this unprecedented ML demand. Let's imagine what that might look like. Imagine a world where the scaling is in fact more balanced, where we can get another 10 to 50 times improvement on process and architecture that is truly scalable. Is this even possible? We believe it is, but only if you think about the problem differently. By thinking outside the traditional box and with true end-to-end co-design, we believe this is possible. In this talk, I'm going to highlight some of the possibilities when you truly embrace this extreme co-design approach. So first, let's start with process. As I said, Moore's law is alive and well, but can we amplify it even further? Well, historically, transistor density improvements, they've been amplified further with gradual increases in die size. On the right, there's a plot showing die sizes over the last several decades. And as you can see, there is a steady increase. But we're hitting a wall now, and die sizes are not really getting much larger. And there are a few primary reasons for this. The first is that large chips have low yield. The second is that there are fundamental challenges in lithography that prevent increasing the reticle size. And then lastly, larger chips are just significantly more difficult to power and to cool. But the industry has been creative in finding ways to extend beyond the single die and solving some of these problems. Here are some examples. With advanced chiplets and MCM techniques, we're seeing maybe 2 to 5 times more silicon area in a single device. And recently, we've been really encouraged by early announcements of concepts using advanced interposer techniques, even using an entire wafer as an interposer by Tesla. These techniques, when they become available, might achieve another 20 times more silicon area in a single device. And we believe these techniques are highly valuable because they extend the effective size of the chip. Now let me show you how we've approached this problem at Cerebras to show that it's even possible to push further with tight co-design. In 2019, we introduced the Wafer-scale engine. And last year, we announced the second generation. This is the single largest chip ever built. It's 56 times larger than the largest GPU today. And it's a single piece of silicon. It's the largest square that you can carve out of a round 300mm wafer. At over 46,000 square millimeters in size, it has 2.6 trillion transistors. And with that, we can fit 850,000 compute cores. And with all of those cores integrated onto a single piece of silicon, we can get some truly mind-boggling numbers for memory and fabric performance. And that's because everything is on chip. Now, to do this requires deep co-design to solve those 3 main problems of yield, process, and power. Yield is a problem even for traditional chips, so it becomes a fundamental challenge for extremely large chips. At the wafer level, it would be literally impossible to yield a full wafer with 0 defects, because defects in silicon and in manufacturing, they're just a fact of life and they cannot be avoided even in mature processes. So to solve the yield problem, we use redundancy. We architected our chip as a giant array of uniform small cores connected with a 2D mesh fabric. And the design includes redundant cores and redundant links. The picture shows an example. There are redundant cores that are built into the hardware, and these are shown at the top in that light yellow color. On the left, when there's no defects, the redundant cores, they're not used. And on the right, when there is a defect, we use a redundant core to take its place, and then we reconnect the entire fabric with the redundant fabric links. And this fully restores the logical 2D mesh fabric. With this technique, we can drive yields very high at very low additional cost. But this is only possible because of co-design. It's co-design with the chip architecture. In fact, as you can see, the yield solution is baked deeply into the fundamentals of the fabric design itself. The second major problem is how do you extend beyond traditional lithography limits? Creating larger reticles, unfortunately, has some fundamental challenges. So instead, we worked within the standard independent die structure on a single wafer. But instead of cutting up all of these individual chips, we cut out the largest square from the round wafer. In a standard fab process, these independent die, they're separated by what's called scribe lines. And these are used for mechanical barriers and test structures. But instead, we add wires to cross these scribe lines to connect these otherwise independent die. And we do this using high-level metal layers. And this extends the 2D mesh fabric across the entire wafer, resulting in fully homogeneous array of cores at the wafer level. And as you can probably already tell, this is only possible with tight co-design between the fab, TSMC, and the chip architecture. These seemingly simple short wires, they're a huge deal because they provide the same bandwidth within a die, but across the entire wafer. And that's only possible because we're spanning less than 1 millimeter of distance on silicon. And for chip designers, we do this all the time without even thinking about it. When you compare that to traditional SerDes-based techniques, the difference is really just massive. And it's because it's just physics. Driving bits less than 1 millimeter on chip is much, much easier than through a package, through connectors, through circuit boards, and sometimes even cables. And the result is orders of magnitude improvements compared to traditional IOs, as you can see in the table. We're able to achieve about an order of magnitude more bandwidth per unit area and almost 2 orders of magnitude better power efficiency per bit. But there really is a clear trade-off here. In many ways, by moving the communication problem onto the chip, we've made it easier. But we've shifted some of that complexity that would have otherwise been in the chip in the form of SerDes. We shifted that complexity into the package. So this can only be done with extremely tight co-design with the package and the system around it. And at the package level, what we've done is we've taken all of this silicon that would have been traditionally spread out physically into different servers or even different racks, and we've moved it all into a central concentrated location. And all of it consumes on the order of 20 kilowatts of power. Now that concentrated high density exceeds what traditional power and cooling capabilities can do significantly. So first, we need to bring the power in. And in traditional current distribution, it's done through power planes in the circuit board, as shown in the cross-section figure on the right. But the current densities are simply too high to distribute laterally through the circuit board. If we did that, we'd only be able to power the edges of the wafer. Now, once you get the power in, you have to get it out in the form of heat. And traditional cooling is done through direct airflow. But again, the heat density is too high for this to be effective. If we did that, again, we'd only be cooling the edges of the wafer. So here, the solution was to co-design a 3D package. We can bring the current in perpendicular to the wafer by going directly through the PCB. And then we bring the heat out perpendicular to the wafer by using water flow through a cold plate. And this solution allows us to power and to cool every die evenly, both at the edges and the middle of the wafer. But as you can already see, this is not your typical package. So it needs to be co-designed with the full system around it. And this is what that looks like. We start with the wafer, and that's held vertically. Then it's surrounded by what we call the engine block. This is the subsystem that holds the wafer and is really the package around the wafer. We bring the power in from the front, again, perpendicular to the wafer. And then we take the heat out from the back through the cold plate and a manifold to direct the water flow. And lastly, we build the entire system around this engine block. And here, the entire system architecture is co-designed to support that wafer-scale chip and the engine block. The power supplies are on the front, right next to the water pumps, and there's a heat exchanger below to remove the heat externally. Power comes in from the front, again, all perpendicular to the wafer. The wafer generates the heat, and then the heat is removed through the water being pumped through the cold plate and into the heat exchanger below to be removed from the system. And then lastly, the cool water is recirculated back to the wafer, and this forms a fully contained internal water loop. And this is what the full system looks like. This is a system where every detail is co-designed to enable a chip that's 56 times larger than traditional chips. And with this level of co-design between the system, the package, the fab, and the chip architecture, we can literally push the envelope of die size well beyond traditional scaling. And we believe co-designed approaches such as wafer-scale chips and other novel packaging, they're a critical part to solving this grand challenge in front of us. This is what enables us to push process gains by as much as 2 orders of magnitude and achieve cluster scale performance on a single chip. Now that's the first component of solving this grand ML challenge. So next, let's look at the next component. That's architecture performance. So imagine what's achievable if we could design an architecture from the ground up for neural networks. Neural networks are generally expressed as a series of matrix multiply or gem operations. And this is very valuable and a simple way of expressing this computation. But as a result, architectures have evolved to run dense gem matrix multiply operations at higher and higher densities. This is actually one of the primary sources of architecture improvement in the industry, and it's part of that 3x speed up that I showed you in the last couple of years. But can we continue this approach and get another order of magnitude or more speed up going forward? Unfortunately, I think that's quite unlikely because both the physical and the power considerations means you can fit only so many fmax circuits onto a single chip. And as you build larger and larger gem data paths, the larger the penalty is if your workload doesn't fit exactly. So in fact, as the data path increases in size, the utilization can actually drop. To get significant gains, we think you need to change the rules. What if you could get the same results, but with fewer flops? Is that possible? It actually is. And that's because neural networks are naturally sparse. And thinking of them as just dense gem matrix multiplies is missing some fundamental properties of neural networks. Sparsity arises when there are zeros in computation. And the main operation in neural networks is a multiply accumulate. And multiply accumulate by 0 doesn't change the result at all. Sparsity can arise in neural networks for so many reasons. Sometimes it's from common ML techniques like ReLU, dropout, and sometimes there's sparsity when you might not even expect it. For example, there are nonlinears that introduce sparsity in the backward pass when the forward pass is otherwise dense. And in addition, even fully dense neural networks can be made sparse. In fact, inducing sparsity is often done in inference already. And it's really not surprising because from an intuitive sense, neural networks are, by definition, over-parameterized. The act of training, in some sense, is really just trying to discover which of the parameters are important and which are not. And the ML community is inventing techniques to exploit this property every day. I've listed a few examples of sparsity algorithms in this table, and they're showing sometimes up to 10 times flop reduction. Imagine if the architecture could harness this potential and enable the ML community to innovate on yet newer and sparser models. That would be a level of ML and hardware co-design that simply isn't possible with existing approaches. That's because traditional gem matrix multiply architectures are fundamentally at odds with the fine-grained, unstructured dynamic computation of sparsity. And there are really two reasons for this. The first is that traditional architectures use caching and local registers to exploit high degrees of data reuse. And this works pretty well for dense matrix multiply because there's a lot of data reuse. The second reason is that these data paths are physically hardwired to perform structured matrix multiplication. And again, this structure works really well for dense matrix multiply because it enables a very compact and efficient design. However, these become fundamental limitations when there's unstructured sparsity. And that's because the sparse operations don't have data reuse and it's not structured. Now, what if we could co-design an architecture with sparsity as a first-class citizen, and we can solve these two fundamental constraints and open up the vast opportunity for ML co-design and sparsity acceleration? There's really a large spectrum of ways to solve sparsity at different granularities, but let me show you how we've addressed these two fundamental limitations at Cerebras to demonstrate what's possible and that you can accelerate even the most fine-grained dynamic sparsity. So first, let's look at memory bandwidth. The traditional memory architectures, they use shared central memory. And that's slow and it's far away when you compare it to the compute performance. Even with advanced bleeding edge techniques like silicon interposers and HBM, the relative bandwidth from the memory is significantly lower than the core data path bandwidth. It's very common for the compute data paths to have 100 times more bandwidth than the memory. What this means is that every operand from main memory has to be used at least 100 times in the data path to keep the utilization high. And the traditional way of doing this is by using data reuse through caching and local registers and accumulators. However, there is actually a way to get full memory bandwidth to the data path. And that's by fully distributing the memory right where it's being used. This enables memory bandwidth that is equal to the operand bandwidth of the core compute data path. And this is only possible with co-design with the system and the machine learning. On the system side, by using wafer-scale integration, we can get high capacity at orders of magnitude higher performance without orders of magnitude higher cost or power. And just like the interconnect, it's just physics. Driving these bits tens of microns from the local memory to the data path, all of it on silicon, is much easier than through a package to an external device. And on the ML side, this level of memory bandwidth enables some truly remarkable capabilities. With full memory bandwidth, we can run matrix operations at full performance across all blast levels, whereas traditional gem architectures with low memory bandwidth are restricted to running only matrix multiply at full performance. In fact, you can see that any blast level below matrix multiply requires a massive jump in memory bandwidth, which just isn't possible with traditional memory architectures. But with enough bandwidth, you can run full performance all the way down to AXB, which is the vector scalar multiply. And that's important because a sparse gem is just a collection of AXP operations, one operation for every non-zero element. And with this capability, it's possible to accelerate any sparse matrix multiply, even for completely arbitrary, unstructured sparsity. Now that we have the necessary memory bandwidth, the second fundamental challenge is how do you handle the dynamic unstructured sparsity? For that, we use fine-grained data flow scheduling. And that's where all of the computation is triggered by the data. In the Cerebras core, the fabric transports data and control information in the hardware. And once the core receives that data, it triggers the tensor instruction to run. With this data flow mechanism in the core, the entire compute fabric is a data flow engine. And this data flow engine enables native sparsity harvesting because you can simply filter out all the zero data at the sender. Since all of the computation is triggered by the data, if the sender doesn't send any data, the receiver doesn't perform any compute. It's really that simple. Not only do we save all of the power because we're not performing all of the wasted operations, but we can also get acceleration by skipping the wasteful work and using those cycles to perform the next useful work. Now again, this is possible only with tight co-design with the machine learning and the compiler and kernel software. On the machine learning side, this natively accelerates natural sparsity, but also enables co-design of newer, novel, sparse machine learning models. And on the software side, we co-design the software to be data flow aware from the ground up. Let me show you what that looks like. Let's look at a sparse matrix multiply as an example. We consider the entire wafer as a single giant sparse matrix multiply array. And here's how that works. We start with activations distributed across the entire wafer's on-chip memory. And then we stream weights through. As they stream through, they trigger multiplication with the local activations, one individual weight at a time. This is where we're using that fine-grained data flow mechanism built into the core to perform one AXP vector scalar multiply for every weight as it streams through. And we skip all of the zero weights. And all of the full memory bandwidth is what enables this at full performance. The resulting partial sums are then accumulated across the high bandwidth fabric, again across the entire wafer. And there's no need to block or to partition the wafer, because the sheer size of the wafer, we can operate on the full range of matrix sizes. And then finally, this same flow is what we use for both dense and sparse operations. And here are some of the results. In our lab, we've measured speedup of fully unstructured weight sparsity on GPT-3 size layers. All the way up to 90% sparsity. That's 10 times more zeros than non-zeros. And on the right, you can see our lab results showing near linear speedup even at this extreme level of sparsity. The only limitation really is Amdahl's law, because you have to amortize fixed overheads. But our massive memory and interconnect bandwidth enables us to reduce that overhead significantly. And the overhead actually reduces further as the model size grows. So these results demonstrate that we can, in fact, accelerate fully unstructured sparsity, which is not possible in traditional GEM architectures, and therefore accelerate all types of machine learning sparsity algorithms that are already available today, but also enable a completely new class of smarter, sparser models that are actively being developed by the ML community. Now, we as a community, it's only through this level of ML co-design that we believe we can practically reach extreme scale models, and we can break free from traditional brute force flop scaling. In fact, we believe that sparsity opportunities, they only increase as the model size grows. So coming back to the grand challenge in front of us, with techniques like sparsity enabling deep ML co-design, along with traditional architecture improvements, there is a path to driving an order of magnitude or more architecture performance. By changing the rules, we can go beyond just flops, and we can enable an entirely new class of sparse ML techniques co-designed with the ML community. That's just not possible otherwise. All right. We've addressed 2 out of the 3 major components to scaling performance. So let's talk about the last component, cluster scale out. Clustering solutions already exist today, but why is it still so hard to scale? But to understand why, let's look at existing scale-out techniques. The most common is called data parallel. And here the model is replicated in each of the devices, and the training data is simply split across the devices. This makes it the simplest approach. But it doesn't work very well for large models because the entire model needs to fit in a single device. So to solve that, the common approach is to run pipelined model parallel. And this is where you split the model and you run different layers on different devices as a pipeline. And this enables larger models because you can use all of the memory across your devices, but has significant communication overhead. And as you spread across more devices, the activation memory needed for training increases quadratically because you need to keep the entire pipeline full. So to avoid that, it's also common to run another form of model parallel by splitting the layers across devices. But this also has communication overheads, and splitting these layers can get complicated. So because of all of these constraints, there really is not only a single one-size-fits-all way of scaling out today. In fact, in most cases, training massive models requires a hybrid approach with both data parallel and model parallel. This is actually how OpenAI trained GPT-3, for example. So although scale-out solutions do technically exist, there are so many limitations and they're very complicated that often they're not accessible to the ML community. And the fundamental reason for this is actually pretty simple. It's because in traditional scale-out, memory and compute, they're tied to each other. And trying to run a single model on thousands of devices, it turns the scaling of both memory and compute into distributed constraint problems that are interdependent. As the model size grows, we need to do more partitioning of the model onto more chips and do more fine-grained coordination and more synchronization. If you've trained a neural network on a large cluster of GPUs before, you will know what I mean. In fact, large companies like Google or Microsoft, they have entire engineering teams to figure out how to do this for their large models. To solve this problem properly, we believe it's not about creating software solutions to hide that complexity, but by truly co-designing a solution at the cluster level and thinking outside the traditional individual device. We believe it's possible to architect a solution that's inherently simple and scalable. So let me show you the approach that we're taking at Cerebras to demonstrate what's possible. It's possible to think about the entire cluster as the ML accelerator. And when you do that, you can architect the cluster level memory and the cluster level compute in a more natural and scalable way. At Cerebras, we're doing this in an execution model we call weight streaming. We start by first separating out the memory from the compute, fundamentally disaggregating them. And the reason you can do this is because neural networks use memory differently for different components of the model. So at the cluster level, you can design purpose-built solutions for each type of memory and each type of compute. And as a result, you can untangle them and completely simplify the scaling problem. So let's see what that looks like. The primary compute unit is the Cerebras CS2 system. With that single large wafer-scale chip, it is the large foundational building block on which all large model layers can run without partitioning. To that, we add an external unit to handle the models of extreme size, and we call this external unit MemoryX. It's designed specifically to scale to extreme model sizes, capable of supporting up to trillions of neural network weights. Now, independent of that memory, we introduced an interconnect to scale up the number of CS2 systems. We call this Swarmx, and it's specifically designed to scale neural network training and cluster up to tens to hundreds of systems. In this execution mode, all of the model weights are stored centrally in that MemoryX unit. And then they're streamed onto the CS2 system as they're needed to compute each layer of the network, one layer at a time. The weights are not stored on the CS2, not even temporarily. As they stream through, the CS2 performs the computation using the data flow mechanisms, and the resulting activations stay resident on the CS2 system, ready for the next layer. And then on the backward pass, the gradients are streamed back in the reverse direction, back to the MemoryX unit, where we do the weight update. So you can think of this as designing a purpose-built memory hierarchy at the cluster level. Now, to do this, you need to be careful, because in general, moving data further away from compute can hurt performance if you're not careful with latency. But like I said, not all memory in neural networks is being used for the same thing. Activation memory has to be accessed immediately by the next neural network layer. That makes it latency sensitive, so we keep it on chip. But weight memory, on the other hand, is used and updated relatively infrequently. There's no back-to-back dependencies. So we exploit these two properties. First, we use coarse-grained pipelining. And this avoids the dependencies between layers by scheduling the entire training as a pipeline of layers. We can start streaming weights for a layer without having to wait for the previous layer to complete. And as with any pipeline, this enables high performance while not being sensitive to latency. And secondly, to cover the dependency between training iterations, we can actually overlap the weight update with the forward pass of the same layer. And this forms a fine-grained pipeline of the updated weight matrix with the forward pass that's consuming it. And since the CS2 is processing the weights individually, one element at a time, we can stream out the weights immediately after they're updated. So the forward pass can proceed without having to wait for the entire weight matrix to be updated. And by using these pipelining techniques at the cluster level, the weight streaming execution model can hide the extra latency from external weights and hit the same performance as if the weights were locally stored on the wafer. And to solve the problem of storage capacity, our architecture moves all of the model parameters into that single device, the memory X. By moving the memory further from the compute, it makes it possible for us to use both DRAM and flash storage to support extremely large model sizes in a single subsystem. The memory X unit also has internal compute to perform the weight update and optimizer functions. Just like we did for memory, we're separating out the compute that's operating on the weights to be close to the weights. And since the weight computations are extremely small compared to the main model execution, we can still efficiently perform these updates externally while the main model runs in parallel on the CS2. Now, with this approach, we can provide flexible capacity to store up to extreme scale models. And then we can scale the compute completely independently by simply clustering multiple systems together with a specially designed interconnect for data parallel. We call this Swarmx, and it sits between the memory X units and the CS2 systems, but it's really independent from both. Swarmx broadcasts the weights to all the CS2s, and then it reduces the gradients back from all the CS2s. So in some sense, it's more than just an interconnect because it's an active component in the training process. Internally, Swarmx uses a tree topology to enable very modular and low overhead scaling. And because it's modular and it's disaggregated, you can scale to any number of CS2 systems with exactly the same execution model as a single system. And lastly, since the underlying hardware architecture supports sparsity natively, the cluster also supports sparsity natively. Sparsity can be induced in the weight matrix within the memory X unit, and then the sparse weights are streamed to the CS2s. The Swarmx interconnect broadcasts them all in sparse form, and the CS2 processes them and performs the computation all in sparse form. All of this happens natively with no change to the weight streaming model, and in fact, it's exactly the same flow that we use for dense. Now, with this interconnect architecture, in combination with the pipelining techniques that I described, we project near linear scaling from a single CS2 all the way to 192 CS2 systems. And this is how that translates to training speedup for a range of natural language models. This is using the scaling laws for NLP models that was published by OpenAI. And as you can see, the scaling is near linear, mostly falling off for relatively smaller models where the batch size becomes a limitation beyond a certain point. But for relatively large models, especially these extremely large models, we can expect near linear scaling all the way to tens to hundreds of systems. So, as you can see, by changing the rules, by thinking beyond the individual devices and thinking holistically at the cluster level, it's possible to solve the fundamental challenges of scale out today. And it's possible to execute exactly the same as on a single device as for hundreds of devices. And that's how it's possible to address the final component of the grand ML demand challenge in front of us. Scale out that's actually inherently scalable. So now let's go back to where we all got started today. In the past couple of years, we have seen over 1,000 times greater demand from the ML workloads, and there's no signs of slowing down. In the next couple of years, this is where we're going to be. On first glance, this might seem daunting and not possible. But what we've seen today is that it is in fact possible, but not by using traditional techniques. It's only possible if you change the rules, only if you think outside of the traditional boundaries. we believe this future is achievable. And it's only achievable with deep co-design. With co-design, we can do some truly remarkable things. It's possible to build chips beyond individual die, to push beyond just brute force flops, and to design an architecture that is inherently cluster scale performance. When you step back, what an exciting time it is to be a computer architect. I've shared with you today just some of the approaches that we're taking at Cerebras to pursue this future, really as an example of what's possible. And I'm really looking forward to seeing what we as a community come up with next. Thank you very much.
Thank you very much, Sean, for that inspiring and very informative talk. I really appreciate it. I think at this point, I would like to open the floor for questions. Maybe I have a lot of questions, but I don't want to be the, let's say, question hog. But maybe I'll start it with so that people can keep thinking of questions like pipelining, as you mentioned, right? So I have many questions, but a few interesting things come to mind. I really like the approach you're taking, rethinking the entire system, because it doesn't seem like there's a better way, let's say. Clearly, this is a huge chip. Can you talk a little bit about like what goes into validating and verifying it?
Yeah, so there's one of the enablers for the yield mechanism that I described is you need to have a fairly extensive strategy to be able to identify when you have problems so that you can then work around them and map them out using those redundant cores and redundant fabric links. And so for that, we have developed a very parallel yet fine-grained way of testing almost all of the wafer at the same time. And that becomes a fundamental enabler for us to use the redundancy mechanisms. There's a few considerations there. When you traditionally do testing of chips, say on a tester, there are power constraints, for example. So when you are trying to do this at extremely large scale, you have many limitations within the traditional infrastructure that you need to figure out how to work around. And so we've developed a lot of custom processes and custom infrastructure for us to be able to do things at this scale. And that's just kind of one example. But ultimately, it ends up affecting pretty much the entire, downstream. Even after you get the chip out of the fab, there's many traditional steps that you would take. Pretty much all of those steps had to be modified to be able to accommodate a chip of this size and this power density.
Yeah, that makes sense. Thank you. One more question related to this before we take some other questions is, maybe you cannot fully answer this, of course, but I'm curious, how much redundancy do you have in the system, in the chip?
So that's a good question. The way we've designed it actually is that those redundant cores are not actually any different than regular cores. And so the level of redundancy is really a matter of programming, so to speak. It's a decision that we can make after the fact as to which cores we use for redundant cores. And so that is a really nice architecture property because it doesn't lock you in to a fixed ratio and you can adapt to different process variations, and depending on if you're on a more mature process versus a more bleeding edge process, the defect densities can change quite dramatically, and so the architecture can be flexible to that. Now, having said that, just a rough number, just to give you a sense, at a wafer level, it's not uncommon to have maybe hundreds of defects, and so you can get a sense of the number of redundant cores that we would need to be able to accommodate that. It's not very high. It's a pretty small fraction of the total number of cores that we have.
Okay, thanks. And one last question related to this maybe is, so do you also reconfigure during online operation, or do you use the redundancy to get rid of, let's say, hard faults only?
We use it to get rid of hard faults only. However, if faults happen to develop post manufacturing, we can reconfigure to work around those new faults, but we do not do anything like fully dynamically while the workload is running.
Okay, great, thank you. Now I think it'd be good to have some other questions. You can either raise your hand so that you can speak, especially Zoom participants. And I think there are already some questions accumulating on Zoom. I haven't checked YouTube, but maybe I'll ask Juan to check YouTube also.
Do you want me to check the questions? Or
no, I can
moderate?
Yeah, I can moderate, I can read it, but feel free to check the questions if you would like also in Zoom. So there's one question related to testing again from Behzad. It says, when a defective core is detected, how much cost, performance, power needs to be expended to utilize the redundant cores? If it's not negligible, have you thought of taking advantage of the fact that DNNs are resilient and can naturally hide some errors?
That's a really great question. So there's two aspects. The first, in terms of the cost and the overhead of using these redundant cores, the cost is actually quite low. Especially if you think about it from the power perspective, because all the redundant cores are not active until they're put into action, right? And so you can reserve all of these redundant cores, so it's virtually no impact to your overall power. But having said that, we have considered whether we may actually be able to live with some level of defect. And I do think that in general, this is a very interesting, relatively unexplored space right now. We have chosen not to exploit that, primarily for a couple of reasons. One is that it becomes, I think, reasonably challenging to characterize how this would impact the neural networks. What level of defect and density and what type of defects and all that would and what the impact would be on the final neural network training is something that needs to be characterized, which we have not done, but I think would be a quite interesting problem to solve. But the other one is more practical in nature. As we're trying to build a very reliable product, it becomes increasingly important to have very predictable outcomes in your tests. And so we've taken a fairly strong stance there, and don't want any different results if you're running from different system to a different system, as an example. And so that makes the actual engineering significantly more robust and more reliable. And that's perhaps the primary reason we haven't really explored trying to exploit this property in neural networks. But I do believe that it's a large there's a large potential there, which is probably worth exploring.
Okay, thank you, Sean. Let me move to the next question. Jan asks, is it justifiable to build a chip using around 20 kilowatts and clustering a lot of these together? This results in large power consumption, which might be difficult to justify from an environmental standpoint. Training large models with large clusters use a very large amount of power. Are you also working on ways to reduce the power consumption?
That's a really great insight. We didn't talk too much about it today, but I agree with you. This is a really big problem. Even if you can train these models and you figure out the architecture to be able to scale, the amount of power to train even a single model today at these bleeding edge sizes is probably not sustainable. It's definitely not good for the environment. But pretty soon you'll need entire power plants to like power one of these data centers just to train like a single model, which is clearly not a place we want to be in. And so I actually believe that one of the main ways that we can address this is that we have to, as a community, and this is where the co-design with the machine learning becomes very important, is as a community, we have to find ways to be more flop efficient. We need to find ways to get the same type of results that you might get with a model that's 1 trillion parameters in size, but you only use the flops equivalent of a model, say that's 50 billion parameters. And I think there's a lot of potential there, and this is where all the sparsity and the unstructured dynamic computation comes in, is that we believe that it's through those kinds of mechanisms that can enable us to come up, us meaning the broader ML community, to come up with more efficient machine learning neural network architectures. Honestly, I think that's the only way in the long term, because your point is absolutely right. The power is not sustainable.
Yeah, thanks, Sean. I definitely agree with you on this one for sure, and it's a bit it's daunting, as you said, to see these models grow in terms of complexity, size, and power consumption, performance requirements. One question related to this: do you see any efforts that look promising at the scale or with the goals of course, the cutting edge models? Do you think there's any approach that may be promising in the community?
We're seeing a lot of very promising approaches, and what's I think been actually perhaps not entirely surprising is that it turns out that there's, I think, a lot of low-hanging fruit, if you will, since this entire field is largely unexplored outside of a few ML research labs, is that it turns out that there are some relatively simple things that you can do to sparsify neural networks, and still get very similar or the same final output, same final accuracy. And what I believe is holding us back on this ML research, quite frankly, is that there really isn't hardware today that can actually be used to experiment. And so as an example, all of the machine learning research in this field, some of it even done by companies like Google, are all published on very small neural network models. And in those models, you see quite a bit of potential. but there isn't anything published on any larger models, and really it's just because there's no way for these researchers to actually run those, right? If you run such a large model, and you induce a bunch of sparsity, but your hardware doesn't give you any speed up, you're just running it at the same speed or even slower, right? And so there's a bit of a like at the industry level, at the community level, I think there's a little bit of a chicken egg problem that we have, right? Is that, you know, these neural networks are so large now that there's a very tight dependency on the hardware, and without hardware that enables that research, that research won't happen, right? And so that's a big part of what we believe Cerebras' mission is to enable some of that research. And so we are seeing quite a lot of promise here, and we expect that as more and more research can be done on systems like Cerebras, we're going to see even more, you know, promising results.
Yeah, thank you. That makes a lot of sense. Related to what you said, I have one question. You mentioned some of the projections that you provided are based on OpenAI scaling models. How accurate are those?
So those models have been proven by OpenAI in their paper to be relatively accurate to the model sizes that are available today, right? And so that seems to indicate that it should scale beyond, but you know, today when OpenAI published that paper, the largest model I think was GPT-3, which is 175 billion, and so they showed that their model is pretty accurate up to that point. Now, how much further that scales, I think, is to be seen. Even the authors of the paper, I think, acknowledged that you know, the scaling may not necessarily continue exactly as is, obviously not indefinitely, right? But where exactly does that start to fall off? It's unclear. But the reason why there's so much interest in the ML community today to train these large models is that so far it doesn't seem like we're nearing the, you know, the end of that scaling, right? Right, like I mentioned, Microsoft just trained a 500 billion parameter model, which is like 3 times larger than the OpenAI GPT-3. I mean, I'm sure some of it was just so they could claim that they could do it, but I think for the most part, it's because the results continue to get better. The accuracy of the model continues to get better, and so it does feel like it. You know, we are still not close to the end of that scaling, but it's one of the things that, you know, until you do it, I don't think you'll really know.
Sure, and certainly real hardware will help test some of these, as you mentioned. I'll go back to some of the audience questions, and if people want to ask, speaking up, feel free to raise your hand. Christina asks, in the disaggregated system, how do you handle worker failures or memory X component failures during runtime, for example, training? Have you co-designed fault tolerance approaches with the underlying disaggregated system?
That is a really great question, because at the scale that we're talking about, just the sheer number of components means that you will be getting failures while you're training, right? A sheer number of components, as well as the sheer size of these neural networks, right? So these are not things that you will be able to complete training within a few minutes, right? These are going to take likely weeks or perhaps even months to train a neural network. And so when you multiply all those things together, the likelihood of a failure, hardware as well as software failure, becomes something you have to accommodate in the architecture. And so we've architected both the hardware and the software to have redundancy. So as an example, although I showed the MemoryX unit as a single monolithic block, it's internally actually made of many distributed smaller components. And so if any of those components fail, we can basically remove it out of the overall pool, and we can remap the workload and the weights to the other components. And so that can be used both in a kind of fail in place model where your performance can degrade a little bit if you fail, or you can essentially add some redundant components that are unused normally, and then you basically put them into service once a defect is detected. And that type of kind of architecture direction is there throughout the entire cluster design. It's in the Swarmx interconnect as well, all the way down into the CS2 system. When you're building a cluster of potentially tens or hundreds of CS2 systems, you could have a whole system, for example, go down, and you need to be able to handle that as well.
Okay, thanks. There's one more question on Zoom. Sebastian asks 2 questions. Let me ask the first one. How did switching noise affect the layout of the individual cores, and what solutions are you employing to mitigate it?
So there's probably 2 different aspects to that. One is at the kind of micro level, when you look at a local region of cores, the overall switching between the cores and within the cores is actually not very different than a traditional CPU, multi-core CPU, for example. And that's to say that it's actually not too bad. Everything is relatively distributed, and there's quite a bit of randomness introduced into the whole thing because of all the different control logic and the fact that these cores are actually completely independent. And so there really isn't any special consideration beyond the standard physical design techniques there. However, when you zoom out a little bit more and you get into the hundreds or thousands of cores range, then you have to start being careful that you don't create overall patterns between all of these cores that might put like undue stress on your power. For example, a very obvious area is on the clocks, for example, right? If you're clocking all of these cores all with a synchronous clock, you got to make sure that you're not causing undue noise and power stress from all of those clocks firing at all these apps at the same time. And then there's also at the workload level itself, these cores are all independent, but as the workload flows through, right, this is all data flow, and so we think of the workload flowing through kind of in waves. As that wave propagates through, you can have like a wave front of very high activity, which can again, especially when in aggregate across many cores, can definitely put a lot of extra stress on some of the infrastructure, especially the power infrastructure. And so we have techniques there also to kind of I would say more distribute or add some randomness into the activity to be able to spread things out a little bit. Hopefully that answers your question, Sebastian.
Okay, maybe they'll follow up if that's not clear or fully answered. Yes, thank you, he says. So there are some questions about the memory system and the distribution system. Maybe I'll move on to those.
Sure.
One question says, why are the memory system and the distribution system separate devices? You can start with that.
Sure. So there's really one main goal, which led to them being separate devices, is that we wanted the ability to scale the two independently. We wanted the ability to add parameters to the neural network without having to add more compute. Similarly, we wanted to be able to scale the compute without having to change the memory. And there's the kind of practical reason that you want to do that, to provide the flexibility from the product standpoint. But there's also the kind of more fundamental property is that when you enable that, you can then much more easily scale the overall solution. The fact that the memory and the communication are generally tied together in traditional devices, in traditional GPUs, is what ultimately causes all of the complexity in scaling traditional GPUs, because of all of the model parallel and data parallel challenges that I mentioned. So that's ultimately the reason why we ended up creating them both as logically separate, but also physically separate entities.
Okay, thank you. Related to this, I have a question also. Maybe I'll use this opportunity since we're talking about the memory X. So memory X sounds quite interesting, clearly, and you have huge amounts of memory, and you mentioned that it's DRAM plus flash. How much of it is very custom developed in there? Like, can you talk a little bit more about it, basically how you manage it and
Sure.
Yeah, how it works?
Sure. So the first off is that whether or not we use flash depends on the model capacity, and really the only reason for doing that is when you want to scale to these multi-trillion parameter models, and DRAM becomes just relatively cost prohibitive. But otherwise, for all more kind of modest size models, we run entirely DRAM. And internally, the overall structure is pretty straightforward. You need to have enough aggregate DRAM bandwidth to be able to satisfy the overall streaming bandwidth to the CS2. But then internally, because you need to perform the actual weight updates, there's actually quite a few like internal steps that you might need to also do, like casting weights from FP32 to FP16 and things like that, adding sparsity metadata. There's a internal X factor increase in terms of the memory bandwidth that's actually required within that memory X unit. And that's all managed with a very highly tuned software solution. Coming back to the previous question about redundancy and all that, in a highly distributed array of these DRAM and compute and software units. So that's what the kind of high level internals of the memory X unit looks like. It is for the most part not using the DRAM is standard off-the-shelf DRAM. The overall connectivity is also based on standards. So it's not, in that sense, a highly custom solution, but it's the overall, architecture, system level architecture, and the highly tuned specialized software that ultimately, bring this whole thing to life.
Okay, thanks. One more question related to this from YouTube is there potential or scope to introduce in-memory processing techniques in the memory X? Maybe I'll generalize it to ask you your opinion on in-memory accelerators that are coming up in the field. More for inference these days, of course, but there's potential for improvement going into the future, of course.
So yeah, I think that's a very interesting area, in the sense that I think there's potential of thinking about doing in-memory compute in memory X, but in a lot of ways, we actually consider our main, wafer-scale engine as a somewhat in-memory compute device because of how distributed the memory is. And so in general, I think there's a lot of promise in moving in those directions, bringing compute closer and closer to where the memory lives. I think is critical to us solving the performance and the overall power problems. But you gotta right size the solution for the problem, right? And so I think that's one of the themes that I tried to convey today, is that we're ultimately looking for the right solution for the memory architecture for the different types of memory within the neural network computation. Some of the memory, I think, could benefit from more in-memory type processing, and some of the memory, like the weights, for example, in some sense, you actually want to move it further away. And so I think that's the art of doing architecture, right? Is finding that set of trade-offs that work well for your particular requirements and workload. But having said that, when you step back, in general, I think the whole trend and interest in more in-memory compute, I think is really great. And like I said, I very much consider what we're doing at Cerebras as a bit of a step in that direction with our wafer-scale architecture.
Yeah, thanks, John. Yeah, I actually agree with you. When I explain Cerebras in my undergraduate or graduate classes, I think of it as putting memory and compute closer together, and lots of memory, of course, right?
Exactly.
So, one question kind of related to this is more maybe speculative, but what are your thoughts on computational memory through magnetic tunnel junctions or emerging technologies, let's say?
So yeah, I think that in general, there's a lot of very promising emerging technologies, which we as a community need to continue to pursue. I would say that at Cerebras, we're also interested in some of it. However, I will say that I think this is where the difference between industry and research starts to show. Our primary objective is still building product, and so we generally have make a conscious decision to not rely too much on emergent technologies until they've been proven by the industry or perhaps by us to have enough reliability and that they're real enough to build a full product that we can sell around it. And so in that sense, I would say that, and this may not be specifically a Cerebras point, but just a point about companies building product likely, I think will not be at the absolute bleeding edge in terms of emerging technologies, primarily to balance the risk.
Thanks. Let me see. I don't want to miss any questions also. There is one question about reconfigurability to achieve efficiency. I think the question is asking whether, how do you see the future of reconfigurable architectures, FPGAs, CGRAs, coarse-grained reconfigurable architectures, and how they play a role in training. Clearly, we've seen systems with FPGAs also, right, built at large scale to do training as well as inference. What are your thoughts?
I think that's the million-dollar question, right? I think that's the crux of what we all as an industry are trying to feel our way through in some sense, right? When you step back, it's really all about trying to find that right level of configurability, right? And this field in particular, I think, is very challenging because of that. Because, you know, on the one extreme end, you could build, you know, some hardwired circuits to perform certain operations. Let's say build a convolution engine that just performs convolution. And without a doubt, if you do the implementation reasonably well, you're not going to be able to do much better than that with something that's more programmable, more flexible. But that's not going to work if the field is changing every single day, right? And the types of models people are running is changing every single day. And so finding that balance between the highly optimized and purpose-built architecture, balancing that with the programmability and flexibility in a lot of ways is kind of the name of the game here. What we've done at Cerebras perhaps is lean a little bit more towards the programmability and flexible and configurability side, in part because we are seeing the level of creativity in the ML community is basically unbounded, and as a result, don't really want to hold that back. And what I mentioned today in terms of the sparsity and being able to accelerate fully unstructured sparsity at fine grain is one example of that. You know, if you instead just decide that you want to build an accelerator which can harvest sparsity, but only very structured sparsity, you come up with a you know, different design. And in fact, at one end of the spectrum, you'd probably look at what NVIDIA has announced with their very structured sparsity in their A100 as an example, right? As an extreme end of that. Without a doubt, that has you know, a certain level of efficiency and you know, and overall design compactness that will look different than if you build something, you know, more flexible. And so here, I think it's really about finding that balance where you think you can enable the ML community to really do something, you know, truly different. And I think this is in a lot of ways why this whole field is so interesting right now. At Cerebras, we believe very heavily that it's going to come from these unstructured techniques and sparsity being one of the major components, and you know, building, you know, large arrays for your data path oftentimes is counter to that. But finding that balance is you know, is something that I think we all as a community are all, you know, trying to feel our way through.
Yeah, it's certainly exciting times to look at many different types of execution models as well as devices to enable a workload like this. I have some more questions. If you have time, I'm happy to ask them. But if you need to go, I understand that also.
No, I think I should have time until maybe a few minutes before the end of the hour.
Okay.
So maybe another 20 minutes or 15 minutes or so.
Okay, that's great then. I'll continue, and people come up with other questions. Feel free to write it or chime in, raise your hand. Okay, there's one question. I think you discussed a little bit about the on-die distributed memory, but someone wants to know Can you elaborate more on the architecture of the on-die distributed memory?
Yeah, I did not dive too deeply in this talk today, but yeah, I can elaborate a little bit more. So we have only one level of memory hierarchy on die, and that is just local memory. So each one of our cores has a local SRAM memory. Think of it as like a level 1 cache, and that has the full performance to the core. And the only way to access memory beyond that is over the fabric. And so there's really only one level of memory hierarchy on the core, on chip. That's ultimately what enables us to get the high memory bandwidth that we want. Now, having said that, I think it is important to note that traditional memory hierarchies with more centralized memories are done for two reasons, at least, right? One is there's a physical constraint. You have an external DRAM chip that you somehow need to connect to and share with all of your internal compute cores. But it's also done as a way of communication, right? You communicate through memory as well. And here in our architecture, we've explicitly decided to separate out the communication into an explicit form through the fabric and not through memory. And that may not actually make sense for all workloads, but for workload like neural networks, where the memory itself is already highly distributed and localized to the compute, it actually works extremely well. And so that's ultimately what led us down that design decision, and why we landed with this design point.
Okay, thank you. Let me see, one more question. This is more at the process level. Somebody's asking, how are masks configured? Since traditionally there are gaps between each die, how are communication links formed between cores?
Good question. So everything within a die, all of the communication between cores within the traditional die is handled in the traditional way. So almost think of that as just a single regular monolithic chip. To span the gap between die, for us to build out the large wafer scale chip, we had to develop a process with TSMC, with the fab, to allow us to essentially span that distance, which is a little less than a millimeter, with high-level metal layers. There's two challenges to that, broadly speaking. The first is more on the lithography front. Today, individual die are essentially like printed, and then it's stepped to the next die, and then stepped to the next die, and so on. And so there is a custom lithography step that needed to be developed for us to essentially print the interconnect between them, right? Which would have normally not actually been allowed or isn't part of the regular process. And so that's a custom step that we designed collaboratively with the fab, with TSMC. The second part of it is more around the process of the manufacturing itself. So normally, that space between the die is used as a mechanical barrier, which we're not really using now because we're not actually, cutting in that space. But it's also used for test structures, which from the chip designer's point of view, we never see, right? Because by the time we get the chips, they've already been cut up those test structures are gone. But they're used by the fab to be able to monitor and control the different phases of the actual manufacturing process. And so we needed to work with them to essentially work out what the changes to the process would be if we ended up covering up those test structures, because that's what happens, right? You're using high-level metal layers, so you effectively cover those test structures at a certain point in the process. And so there's a custom flow that needed to be developed for them. Hopefully that gets to the question that you had.
Yeah, thanks for that informative answer. Maybe if they have more questions, they can ask. Let me see. There are some more questions, but I want to ask one question since maybe many of the questions don't deal with this as much. So clearly there's a lot of effort spent on hardware, but I assume there's some commensurate effort spent on software also. Can you talk a little bit about the software effort to make this happen?
That's a really great point. This talk was obviously quite focused on the hardware, and I did touch a little bit about some of the co-design that we do. But I couldn't agree with you more. In fact, it's not a commensurate effort. Depending on how you count, there's a much larger software effort than hardware. Sometimes when I tell people that as a company, only about a third of our engineers are hardware engineers, whether that's chip or system or packaging. About 2/3 or maybe even more are on the software side. Sometimes that comes as a surprise. But the reason for that is exactly what you mentioned, Nora, is that the software challenge is immense. And here, what we've defined our software as is basically, you can think of it as at the highest level, it's a compiler. It's the software that's required to take the high-level description of the neural network from a machine learning framework like PyTorch or TensorFlow, and through a series of lowering steps, ultimately map it onto the wafer as well as the cluster in a way that it actually runs functionally and with performance. And because you're spanning such a large distance in some sense from the high-level description to ultimately the low-level instructions that need to run on each one of these, hundreds of thousands of cores, it's an immense problem. And so we've developed a lot of techniques that are unique to our architecture. And I'll just highlight maybe a couple of them just to give you guys a sense. One is that our compiler has a very major spatial component to it, which might not normally be considered in a kind of a traditional compiler. And that spatial component basically means that you're not only having to determine how much compute is required and what the actual instructions should be, but you also have to decide where you run those instructions and where you map that memory, because we have a 2D grid fabric. And so a large portion of our compiler is actually shares some similarities with traditional place and route EDA tool like algorithms, because we're ultimately having to spatially map all of these components onto the wafers. So that's one very major aspect to our compiler that's different than, say, a traditional compiler. The other area, which I think is also kind of in the same spirit, is that we have code generation techniques that leverage polyhedral analysis and polyhedral loop analysis for us to be able to automatically generate some of the core kernels, core math kernels that we run on the fabric, right? And so in the way that you can think of a normal compiler, like a normal single core compiler taking a set of nested for loops and figuring out, what's the best way to run that. Should it be unrolled or not, for example, how much unrolling should be done. We effectively have a similar problem, but again, in the spatial domain. And so in some ways, you kind of can think about being able to unroll loops spatially across the fabric. And that's again done leveraging polyhedral style analysis. And so those are just a couple of kind of unique aspects of our software that make the problem very unique and interesting, and of course challenging, which is why ultimately we have a non-trivial amount of effort going into our software as well.
Sure, thank you. And that makes a lot of sense. I wanted to ask this high-level question because I think it's important to clarify the effort, right?
I think it's actually one of the things that you're absolutely right, probably deserves much more attention in general, is that no matter how many flops you put down on a chip, unless you can actually access them, they're not really usable, right? And ultimately that comes down to a software problem.
Sure. Yeah. Okay, let me move to some more of the audience questions. Okay, I see one other question on Zoom. Sebastian asks, concerning the cooling solution, would it be achievable or beneficial to cool the entire system below freezing in order to lower resistances, enable higher clock speeds, lower power draw, etc.?
So this is a very interesting question because it actually touches on one of the fundamental challenges of building bigger and bigger chips. And that is the fact that thermal expansion becomes a significantly more challenging problem than our traditional size chips. And the reason for that is pretty simple, is that the chip itself, silicon, expands at a different rate, vastly different rate than the circuit board or the substrate around it, primarily copper. And when you have a relatively small device, that difference in thermal expansion can be limited. When your device is the size of a wafer like ours, and you can think of the wafer and the substrate as kind of expanding radially from the center, you can imagine that there's a significant amount more displacement at the edges. And so one of the things that we generally do is try as hard as possible to constrain the thermal variation, regardless of what temperature you're actually running at. Because the more variation you have, the more difference you have to accommodate in your package. And then the second thing we do is we've designed a special interface between the wafer and the substrate to be able to accommodate that difference, which would traditionally be too high for a traditional package to accommodate. So anyways, that's a long way of saying that I think there are real benefits for going, say, cooler in temperature, but you have to be very, very careful that your thermal variation doesn't exceed the package limitations. And here, you kind of have to consider everything from, what happens in the temperature when you're shipping the system versus when it's actually running versus when it's idle in the data center and so on. And so there's a lot of those kinds of considerations that go into ultimately how we set our thermal operating points.
Okay, thank you. That's certainly fascinating. I think if you have a large chip like this, you have okay. I think I don't want to keep you too long, but maybe a couple of other questions. One question that's interesting, I think, is do you think there are other workloads that might fit this system well, other than neural networks?
That's a great question, because I think the answer is quite nuanced. I think the answer is both yes and no. On the yes side, the level of memory bandwidth and communication bandwidth that is afforded with this architecture clearly is useful for a lot of workloads beyond neural networks, right? Especially workloads where there's a lot of local communication. Examples could be like stencil-based workloads in the traditional HPC domain. And so we have, in fact, seen some early potential there. We've been even working with a few research labs, which well, I mean, they saw what I just mentioned, and I was like, oh, this should actually work really well for our workloads. And we've been doing some exploration in that space and been seeing some really remarkable results. In fact, I think one or two of them we've even published, and so you should be able to find that. But the reason I say yes and no is because we've designed the architecture very intentionally for neural networks, and so there may be aspects of it which don't necessarily always map cleanly into the requirements needed by all other workloads, right? A very common one that comes up all the time is, well, we don't support double precision numerics. And so if your workload can't fit cleanly into single precision or even better into half precision, like neural networks do, it may not work very well, even if every other aspect of the system architecture might fit the workload well. So I think that's one of the conscious trade-offs that we've made as a company, right? Is that we believe that if you're going to run one workload very well, in this case neural network training, we should design the entire architecture for neural network training. As a result, you might get some properties that happen to map nicely into some other workloads, but you know, but that isn't a primary design objective, and therefore we might see some workloads which kind of fit 80–90% of what we have, but then, you know, the last 10% is in there because it wasn't designed for it.
Okay, great, thank you. I see one more question on Zoom. I'll ask that, and maybe we'll be done. Is that okay?
That sounds great.
Actually, there are more questions, but given that you need to go, I have to limit it. So I'll pick the last one over here. Can we already tell where the maximum for the chip size possibly lies, where it doesn't pay off economically anymore, versus the option of having multiple chips, basically? I think this goes to the heart of what you have described, so maybe you have some opinions.
Yeah. So I think there's two angles to this. The first is it has to do with the yield discussion that we had, right? Traditionally, that trade-off is very dependent on what the yield curve looks like. And traditionally, the way you pick your die size is by trying to optimize your yield. Since we've largely solved that yield problem, it's no longer a first order factor in making that assessment, right? And so to me, it has a lot to do more with what the what all the system level complexity that I exposed you guys all to today, and what that cost is, right? Now, for what we're building, this all makes sense and it works, and the overall economics work out. And the reason I'm saying that is that may not necessarily be the case for all different workloads. And so, you know, in my mind, there's a very, you know, kind of, you know, technical view of the wafer scale and building larger and larger chips and how we've solved it. But in the bigger picture, a lot of things have to kind of come together to enable that, because this way that we've solved this problem works very well for neural networks, for machine learning, may not necessarily work very well in general, even though it's a technical solution, right? And that's when you have to get into all the other aspects of the other requirements for different use cases. And so in those, you know, you might not be looking at yield, but you might be looking at, you know, power consumption, or you might be looking at, you know, system design cost or complexity, right? Because without a doubt, you can see that our very custom system is not your, you know, your everyday high volume, low cost PCBs that, you know, people use in their everyday servers, right? In their pizza box servers, right? And so I think if you step back and you look at this in general, I think those are going to be the determining factors to help you determine where you want to be in that die size once you've solved the yield problem. Hopefully that answers the question. Okay,
thank you very much. That's very clear to me, and hopefully it's clear to others as well. Well,
no, before we wrap up, sorry to interrupt you there. Just a real quick thing. I hope you don't mind.
Yeah, go ahead, please.
Yeah, I did want to just say, you know, thank you so much for having me. This was a pleasure. And as you can probably tell, I always enjoy talking about what we're doing because I think it's really exciting. But I did want to just briefly say that, you know, if any of what I'm saying is interesting to any folks on the call here, you know, we are hiring, and we're always looking for you know, talented full-time as well as interns. And so if you have any interest, I just wanted to, well, we're hiring basically in pretty much all areas, so I won't spend too much time there. But the main thing I wanted to show you is if you have any interest, feel free to reach out to me. Or I've put a link down at the bottom here to Tom Case, who's our head of talent and head of recruiting here. His email is really easy, tom@cerebras.net. So I just wanted to briefly mention that before we wrap up, that if any of this resonates with you and you guys are you know, are interested in exploring intern or full-time job opportunities, we'd love to explore with you.
Yeah, thank you, Sean, and hopefully there will be people excited about everything you said, and I certainly find it inspiring and nice. They may come and work with you, or even if they don't, maybe they will come up with new ideas that
exactly.
that are out of the box and out of the die, or and in general across the stack, let's say, so that they can make a big difference going into the future. Yeah, thank you. I really appreciate you taking time and giving your perspective and certainly what you have done. We look forward to seeing more, and maybe we'll see you again in one of these seminars in the future for another chip. Who knows, right?
Yeah, absolutely. Thank you again for having me.
Yeah, thank you very much. Have a good day.
You too.
Bye-bye. Thank you everyone for joining.
Yeah.
Bye.